Right. Okay. Oh, I went all the way around to the end. So what I want to talk about now is, as I mentioned, one of my interests has been studying fluids and their effects on seismic properties. And we've been at this for quite a while, actually, right? A lot of the data I'm going to show you comes from a master's student when I was back in Alberta named Helen Yam. She was working for Imperial until recently, actually in Calgary. She should have been a PhD kind of person. That's why I had a lot of masters. She should have been PhDs. So it's really, really nice work. And so what I want to show you today is their ultrasonic laboratory experiments from CO2. And the idea is to test how phase transformations change the physical properties and give you kind of a tutorial on some of the interesting aspects of the physical properties of CO2. And then at the end, we've been just dabbling so far with more theoretically with say mixed gases and what that would be, particularly with hydrogen. So hopefully get a paper out by the end of the summer on that. So I'm showing you here CO2. Here's the south pole of Mars, right, which is CO2. But CO2, a lot of you know this already, but there's some actually really interesting implications about the phase state and what that means for what we might or might not be able to detect in seismic. So this is temperature versus pressure for CO2. Basically, this is the phase boundary between gas and liquid. And as a lot of you have heard, there's this phase called supercritical. And this is the critical point. And what's really interesting about CO2 is it happens at such modest pressures and temperatures. So temperature about 31 degrees C and pressure that would only be, say, hydrostatic normal pressure 700 meters down. And so we could, in seismic monitoring, it's possible we could be in any of those phases, depending on depths, temperatures, and whatever. So here's the critical properties of carbon dioxide. It's what supercritical fluid is, just briefly, right? It's not really a liquid and it's not a vapor. It's this interesting material where on a femtosecond level, you've got fluctuations of high density, and it's actually hard to detect. The way to detect it is to you have a glass kind of pressure container and you shine a laser through it. And if it's vapor or liquid, the laser just goes through. But the second it becomes supercritical, it scatters light, right? It's called critical opalescence. And that's how you detect this phase transformation. So it comes along here at about 31 degrees C and 31 degrees C and about 700 or so megapascal, 7 megapascals of pressure. Okay. And just for comparison, methane's more boring. So so at those same temperatures and pressures, methane is already a supercritical fluid. It's supercritical way down at lower temperatures, and we're not really going through any phase transformation. So CO2 is really pretty kind of fun from that perspective, that we can actually see this, and its density is a lot less, and that's water at those conditions. Okay, the same conditions. So what we're going to do is I'm going to focus on, in our lab experiments, exploring what's happening to ultrasonic responses of the rocks within that kind of window of pressure and temperature. We're going to explore the different phase transformations. And so this is a 3D plot of actually the enthalpy, okay, of CO2 versus pressure versus temperature through that zone. And what's interesting here is I go up in pressure, okay. If I was going up along a line like this here, then and I'm at below critical, right? Basically, I hit a cliff. I have that huge phase transformation. There's it takes energy to do it, or it releases energy. You get that. It's a first order phase transition. If I come up here and I go above that supercritical point, then there's no real big jump in the energy or the other physical properties either. And it's much more gradual, so you can kind of walk up that hill pretty easy. Okay, and that's the second order phase transformation. There's actually no energy, entropy, no cliff associated with it. And that has actually implications for seismic monitoring. So let's look at the CO2. Here's just the same thing with densities. I shifted the and the bulk modulus, the adiabatic bulk modulus is the one we need for seismic and fluid density. And we see the cliff in all of those, of course. But then if we get up to supercritical, it's much more general. You know, if I want to hike up instead of climb, then I can do that. And we're going to see that in the data. So gas to liquid phase transition, right? You're off a cliff. It's discontinuous. And a big jump instantly, right? If you put enough energy in. And that's a first order transition, as I said. And the gas to supercritical, it's liquid, right? That's continuous, more or less. And that's a second order phase transition. And same with either of those, right? Gas to supercritical. It's not, and we're going to see it's not as interesting a phase transition from the seismic perspective. So here's the plot that blowing up of pressure versus temperature. This is the gas zone. This is the critical point at that 31 degrees or so and 700 megapascals. And this is where we go liquid and supercritical for the gas. And what we're going to do now is I'm going to explore, we did experiments. We kind of went around the critical point where we changed the properties of pressure and temperature on, well, the results I'm going to show you are in an artificial material, but we've done on a lot of rocks too. And now I just, well, let's see, the experiment looks simple. It was actually pretty challenging. There'd be our core sample. We build our own transducers, right, in this way that you saw yesterday. There's a pressure vessel here, the thermocouples to measure temperature. Basically, we pulse the transducer. On one side, we get a wave coming through, we pick it up here, the P or the S, and measure the waveforms, and we interpret those. We control the pore fluid pressure, and we control the confining pressure on the sample. And we actually, I'm only going to show the CO2 results, but we did it for each of this, let's see, each of the, getting the wrong thing. For each of the samples, right? We did it with the water, kind of, you know, fairly simple fluid, right? With nitrogen gas, with CO2, and with vacuum. We went through the whole, it was a lot of work, right, to do that. But again, I'm only going to show you the CO2 results. Now we do this, for those of you who know about, we talk about the nonlinear properties of rocks. And so what we made sure we were doing when we were doing these was that we did it at a constant effective pressure all the time. If we change the pore fluid pressure, we change the confining pressure. That's to try and keep the pore space as similar as possible without you know, trying to add in the complications of the nonlinear effects of the rocks and all of that. We're trying to keep the pore space constant because we wanted to focus on what the fluids were doing to the material, not what the rock was doing under pressure. Okay, and so everything is basically measured at the same effective confining pressure, right? The difference between the confining pressure and the pore pressure. So keep that in mind. So when I show you changes of pressure, that's going to mean changes on the CO2. Okay, so key points: constant effective pressure, whole bunch of different fluids for comparison. We're in a megahertz, right? I'd love to build an equipment to do, you know, low frequency, but I'm not there. A colleague from China may come here, but need money for that. Anyways, what are the materials we study? I'm going to talk about this stuff, and I'm actually going to. So people were talking about Beal theory last night. This actually works as a Beal medium. Now, don't give me heck about this, but what I want to show you is the amplification of the CO2. So we did this on various rocks. This is what it looks like. It's like 55% porous, incredibly porous, incredibly stiff, very interesting material, right? It's not real, I realize that, okay? Doesn't have cracks in it, actually, which is an interesting thing. And we've done it on various Fontainebleau sandstones. And those are theses. We've done it on Berea sandstone. So Don did, and we've done it on, it's just been published. It's Weyburn carbonates. That was Weyburn, for some of you will know, right, is it's not a, it's an enhanced oil recovery project in Saskatchewan where they've been injecting CO2 for a very long time. And this is kind of a precursor. A lot of the same people are working on what's called Aquastor now, that I was involved with on the border of North Dakota and Saskatchewan on a power plant for CO2 injection. And so we had a lot of studies on that. Okay, so these are the materials. I'm only going to show you the artificial rock. Now this is just a scan. I want to go through in detail a bit more. Here's our phase transformation. Here's the lines where we basically changed the conditions on the rock. And we just went around the critical point of CO2. And I'll show you some of these data in detail. It's just kind of some of the data that we collected. These are ultrasonic waveforms. And so let's start off here. What I want to do, let's explore the gas to liquid phase transition. So first, we're going to look at the results here. We're going to start off with the CO2 as gas. We're going to change the pressure and temperature conditions on the CO2 so that it goes to liquid, okay? And so we're basically climbing, have to put the ropes on and climb up. It takes energy to go in or come out to actually do that. We make that phase transformation. And so we're doing that. Here's the P wave data. And so what I'm plotting it is, this is pore pressure. This is increasing fluid pressure. And so we're starting off down here with the gas. Okay, and that is basically this zone here. And then we go up and it's liquid. And so this is actually kind of interesting. So these are our waveforms. Here's our P wave coming in. As you can see, we approach the phase transformation. The waveforms are lengthening, it's getting slower. And then boom, we go down and we get the phase transition to liquid. And we see actually quite big changes in attenuation and velocity. So people are used to say, oh, it becomes liquid density faster. This isn't the case with CO2 because of the high density of CO2. Okay, so don't get rid of the usual preconceptions you have about seismic properties of gas and liquid when we're dealing with CO2. Okay, so that's that. That's the P wave. And here's the shear wave, very similar behavior. Trust me, there's waveforms in there, just I've got it at the same scale for the shear wave. So we're getting incredibly increased attenuation actually. This is ultrasonic, okay? This isn't seismic, but at changes there. And we're seeing a huge jump in the properties, kind of as we expect, right? Big changes in wave speed, big changes in attenuation. We jumped up that hill. And because fluid density is probably doing most of that for us. So that's the first order phase transformation. Now let's go to liquid to supercritical. So that's going to be up here. Okay, that line. So we're going to start off with liquid and we're going to collect ultrasonic data. Here's the P wave. It's really boring. Okay, there's almost no change. Now remember this CO2, that phase transformation, the second order phase transformation, there's no jump in density, there's no jump in bulk modulus, there's no energy to go across that phase transformation. And look at the waveforms, there's no change in the waveforms at all, right? Doing that. So that's pretty boring. So, I mean, if we were looking for changes, right? Same with the shear waves, okay? We're starting to see changes in the velocities here, right, due to density variations, probably mostly. So almost no change in the properties. And that's where we're going here. And if you look at, this is our fluid density plot, right? That surface, it's pretty flat, so we don't expect. And all the other physical properties too of the CO2 are not changing much. So that's kind of boring. Let's look at now what some of the data looks like. So that's the gas to liquid transition. Oops, I keep hitting the wrong button here. Okay, here's that phase transition line, and we approach it, and then we jump down. There's a little bit of hysteresis here, actually, that you can see. I don't have time to talk about. I think it has to do with the fact that we've got a first order phase transition, and if you've made a measurement every 20 minutes, that's actually not enough time to get energy in and out of even a tiny sample, just thermally. So I think that's what happened. But then we have that. That's this is the velocity of that material dry with vacuum in it. Okay, and that's at 28, and here we're at 40 degrees. And so, oops, we see a change there in the velocity, but it's much more gradual. So when we're going now from gas to supercritical. So that's a P wave. Gas to supercritical is a much more gradual transition, right? Because you did have to hike up the hill in the phase properties in that case, right? There was, you had to put your boots on and take the trail instead of putting on your ropes. And then we could just, walk pretty straight when you're going from liquid to supercritical. So here's now, if I go from the liquid to the supercritical, here's the VP, right? Hardly any change. That's at 25 megapascals, and that's at 7 megapascals. And this is, so here we're basically still close to the supercritical phase transformation, and here we're not, right? So we're seeing basically that change there being much more gradual. So, okay, so the gas to supercritical is a gradual. Gas to liquid is abrupt, and the liquid to gas is an abrupt change. Okay, so and the liquid to supercritical is imperceptible. So, what does that mean for seismic monitoring? We've got, suppose we're out there, we have a leak, pressure changes. We transform from, say, supercritical to liquid or supercritical gas. Can we detect those things? And what I'm going to show now is some calculations, actually. So I'm going to do some modeling first. And we were talking about BO theory last night. So this material actually is a BO medium. And so Helen, when she, I'm looking at that trend here. What I've got here is our actual data. Okay, and that's a lab. The purple area is what I modeled. I modeled with BO theory. The top of it is actually 1 megahertz kind of results. The bottom of it here is what I expect for, say, 100 hertz, right? Gas, and it's basically gas here. Now, so Helen comes back to me. She's made these really nice measurements, incredibly talented woman. And she shows them to me, and one of my colleagues, a guy named John Meanish, who's done a lot of BO theory from the physics side. And he said, why don't you try and model it? So she went and she measured all the parameters you need. I don't want to go into that story. Virtuosity, porosity, permeability, etc. Right? And she modeled it, and she comes and she shows me, basically this plot. And I say, well, something's got to be wrong. When you do rock physics lab measurements, it's very hard to actually get, theory to agree with that. And something's got to be wrong. Go back and do it again. So she went through, made some more measurements, and actually, no, it's good. Right? So she actually got a very good fit of the BO theory to which is a high frequency for fluids to the data, right? And so, we can safely extrapolate. Well, I think I could safely extrapolate that if that's working at 100 megahertz, I can probably take that material if I wanted and pretend I was doing a seismic experiment. So what I did was this is just very simple modeling, right? So CO2 saturated material up there, water saturated, brine saturated material down here. We're going to look at the reflection coefficient from that fluid contact. And we'll look at different trajectories. So look at that trajectory here's what I expect for, just going through the exercise gas phase equation at those low frequencies with that material. What I would expect for the gas to liquid. And of course, it's a pretty big change in reflectivity, as we kind of expect gas to liquid, right? If I do it now for 40 degrees, where I'm now going from gas to supercritical, you can see that it's much more gentle, okay? Remember, here we fell off a cliff, here we could walk up the hill in terms of the physical problem. So maybe with gas to liquid, we could still detect it seismically if there was enough pressure changes. Yeah. So that's that. Do we see similar effects in real rocks? Yeah, but they're muted. Of course, that was 55% porosity. Again, the purpose was to try and understand the effect of the fluids, right? And see if we can see it. So here's stiff hump. This is just one example. Stiff hump in blue sandstone measured up through that zone. Okay, across the liquid to gas transition, and actually cycled through it. So here we started at low fluid pressure, go through the transition, continued up here in the liquid, right, and then we lowered the pressure again, and then bang back again as we cross the gas fluid transition. So we're seeing that transition really nicely there. That's the P wave. And one thing I want to note: this was the first cycle going up, and here is the cycle going down. We're starting to see hysteresis here, and I think it's because we did the measurements too quickly, and I'm not sure we got the full phase transition happening as it should have, but that remains to be seen within that material for further studies. Okay, so that's the CO2 and what the implications might be. Where we're working right now is looking at say mixtures of gas, well, hydrogen, but also mixtures of hydrogen. A lot of you know, right, that we're possibly going to be storing hydrogen because it's hard to store. And one way that's been proposed is we store it underground, much as we do natural gas today, maybe even using the same, aquifers and depleted well reservoirs and that. And so the likelihood that it's going to be mixed gas is probably, at least initially, is going to be high, right? Because our systems aren't set. It's not like you can take your hydrogen and burn it in your oven yet without probably destroying it at some point. And it's probably going to be mixed methane, mixed hydrogen to begin with, that we'll be using, say, to run your furnace in your house, right? Or to run your stove. To begin with. The other thing is hydrogen's still really expensive. And in these, when you put these reservoirs in, it's something called cushion gas, right? So that could be air, that could be methane, that could be other things to maintain the pressure. And so you never take, say, the pressure in these reservoirs below a certain level. So, and you want to use something cheap for that. So we're looking at what the mixes of those might be. And here is, this is basically, I didn't do this. This is, petroleum engineers are much better at finding this information. Okay, this is, what this is if I take different mixtures of going from pure hydrogen to pure methane up there, and I subject it to pressure and temperature, and what is the density going to be, okay, on the side. And when it's mixed gases, it's not so easy necessarily to get that. So other people have done this work and we borrowed it. Now I need to convert that into something that might be interesting from seismic. I don't have time to probably go into all the details, right? But we have to take various derivatives. We have to know the heat capacity and blah, blah, blah to convert this data into something that I can use for seismic, which is an adiabatic modulus. And so we do that. They're kind of boring compared to CO2, right? No fit. They're already both in supercritical under most situations we're going to have, and the mixtures too. There's no phase transitions to worry about, right? Just changes in density and bulk modulus. And so there's how you do it. It takes some derivatives on those surfaces to do it. And I did some this is insanely simple modeling. Okay, all I did was take a very simple geology that might be akin to the Mount Simon sandstone here, where we have a something like the Mount Simon sandstone, right? Porosities and densities, and here is shale, and here is basically basement rocks. Okay, and let's just see what kind of reflectivity changes we might get. I got 3 different cases I'm going to show. It's saturated with brine, saturated with hydrogen, and saturated with methane. And these are just simple. If I did a very simple seismic experiment, I'm looking for the first order reflection from there and the first order reflection from there. Just simple impedance calculations and reflectivity. Okay, so nothing advanced here at all. And at these conditions for the reservoir, 50 megapascals and 40. So if I'm starting off here with just brine, right? Everything's filled with brine to begin with. I'm going to fill this zone in here with gas. And there's the bottom reflection from the metamorphics. Here's the top reflection from the surface of the shale onto the reservoir. And it's not a lot of change. Okay, here if I go down to methane, substitute that out, changes in the amplitude of the reflectivity there, changes in the transit time, but not big. Right? And if I compare that to hydrogen, between those two, right? Really, I can't detect, say, pure methane from pure hydrogen. Unfortunately, so I haven't done any ABO, but I don't think the story's going to change. Right? So it's, yeah, the water velocity is the lowest. Density. OVP. Yeah, it's a density effect again. Yeah. So it's so the density is methane super critical. Yeah. So it's basically the density starts to win out in some of these cases. Yeah. So no, so it's kind of you have to be careful. So yeah, but good thing to know, right? So and didn't see much change, unfortunately. Okay, so that's that. So summary, seismic effects of phase transitions. Where might this work? I guess if a reservoir is leaking, maybe we can detect that phase transition. A lot of times it's already going to be supercritical if it's deep enough, but some of the shallower ones, that might be something we can see, right? One thing I'm thinking about now, and I'm not sure it's been considered, maybe some bottlers have been after this, but the thermal effects start to become pretty important. And the time it takes to get energy, and even through our little samples in the lab, to get those phase transitions to go, takes time. Right? You got to move heat in or you got to move heat out. And that's a slow process. So how is that going to, I don't know, I'm just bringing that up. How is that going to affect the phase transitions in situ in Europe when you got to move heat around to have those happen? And I'm sure somebody's thought of that. So what are the seismic detectability rules? Look at the supercritical, probably impossible. Gas to liquid, a big bang, density driven mostly. We're going to probably see that. And then gas to supercritical, maybe a gradual change in the seismic response that we can pick up. Now mixed H2 with others, we're working on nitrogen and things. If it's already gas, it's probably going to be difficult to see any differences that way. So that's how. So future work, well, we have them carbonates, but more carbonates would be interesting. I'd like to see, how things, the rocks change more, how that affects the seismic response with, say, hydrogen and with CO2, and then maybe some mafic rocks. A lot of people want to use that for geological sequestration too. So that's that, and other fluids maybe we could look at. That's kind of a summary of where we're at, right? We just want some of the, how's the rocks shelf change, dissolution, precipitation of salt, what's chemistry and biology, particularly with the hydrogen, and we're going to be bringing in new phases like H2S, and then working with these mixed gases, which are not necessarily so easy. And then how is that going to change rock strength or friction? these things. So I don't know, we can never evolve all of this. Those are things I hope I can work on for this year's anyways. So thanks for your attention. So questions?
That's the super critical point.